I actually came to US, to Florida, to do my PhD, not to Alabama. And some of the research that I am showing today is from Florida and detecting groundwater discharge in the Florida coast using naturally occurring radioisotopes. But my background is in radiochemistry. I worked for 6 years at the Institute for Nuclear Research and Nuclear Energy in Bulgaria. So I know about man-made isotopes as well. And I just mentioned that my master's degree was in determining plutonium in soil samples. So I'm radiochemist by background. But since I came to US, I decided that I would like to use radioisotopes as tracers instead of my past background is when I was detecting them just from radio protection point of view, how much is in there and is it dangerous for us. But what I'm doing now is I use the signal from radioisotopes to study hydrological and geological processes in nature. So I'm using them now as a tool instead of detecting them from a radio protection point of view. However, I always, my heart would be always in radiochemistry, so every time when I have chance to do something with radio protection, I use the chance, and I will show you an example. When I was a student in Florida, it wasn't part of my dissertation, but I work on radioactivity in drinking water, which is quite an interesting case. And I'll show you some research there. So my outline would be, I'll start actually with introducing some of the radioisotopes that I use. And as I mentioned just now, I will show you an example of, very interesting example of some anomalies of radioactivity in drinking water in US. There are two cases that we study in drinking water in New Jersey and in Florida. And then the last two subjects would be geological applications of radionuclides as tracers, not from radio protection point of view, but just using them for tracers. And some hydrological applications. My PhD was in coastal oceanography, so I use radionuclides to study groundwater discharge, coastal areas, and also to lakes. We actually developed a method which uses radon as a tracer to calculate groundwater discharge to lakes, and I will show you examples of these studies. So everybody knows about this. I just put this slide here because some of my data, specifically for radioactivity in drinking water, will be reported in Pickery. In US, we are old-fashioned and we don't use the becquerel, which I had to learn because I come from Europe and most of my research was in units becquerels, which is discounts per second. But you also will see in some of my reports that I use a DPM, which is discounts per minute. So those are some of the units that you will see in my presentation. So this is just a funny slide that my advisor in Florida, who is also by background radiochemist, although he's hydrologist like me, hydrogeologist, we always laugh about the hormesis effect. Because when we go to measure radioactivity outside, the moment you mention radioactivity and everybody is freaking out and thinking that we put something in the water, few people actually know that radioactivity is all around us, and actually low levels of radioactivity are beneficial for us, and we know this is a hormesis effect. And whether this is true or not, it's still questionable, but back in time, people had these small devices. They had some uranium in them, and they filled them with water, let them saturate with radon that is decaying from the uranium series, and then they drink this water because they thought that this is beneficial for their health. Or they had these uranium bags that they put in places where they had some pain, and they thought that this would help them, and they believed that this helped them. And even today in Europe, we have these cave systems which are very luxurious paths. So people go there and stay just to breathe the radium, so that they believe this will help them to cure some disease. The three groups in nuclides in nature: primordial, these are before the creation; the earth, cosmogenic, that we receive from reactions in the space, and the products fell in earth; and then human produced. So these are mostly products of some accidents around the world, with the most recent in Fukushima in 2011. I'm going to talk about the isotopes that I'm going to talk today are the naturally occurring isotopes from the uranium series. You probably know the uranium-238. We mostly use for hydrological applications radium-226 and the product of radium-226, radium-222, which has a half-life of about 4 days. And this is from the uranium-238 series. From the thorium-232 series, we use the relatively long-lived radium-228 and very intensively radium-224, which is about 4 days again. And I'll show you some applications of the short-lived isotopes. As a PhD student in Florida, I tried to detect radium-220, which has a half-life of 55 seconds, for some specific applications. And one of them is actually detecting contaminations in groundwater, in drinking water. And I'll show you the applications of radium-220, or we radiochemists like to call it thorium. So when I talk about radon, I usually would refer to radium-222 from the uranium-238 series. And when I talk about radium-220, I will call it thorium. It's coming from the thorium-232 chain. And the other, from the uranium-235 chain, I'm going to use radium-223, which is the other short-lived radium isotopes, with half-life of about 11 days. We will see some applications. And first, I'm going to show you the example that I mentioned of tracing radioactivity in drinking water. This was done, as I mentioned, in the US. In the first case that we were alarmed about some interesting cases of radioactivity in drinking water were in New Jersey. And this was back in 2005. As part of the regular monitoring of drinking water in US, the procedure is they first detect gross alpha. So they don't specify what is contributing, they just have certain level. And if this level goes above certain numbers, they start figuring out what is contributing to this gross alpha, what is giving us higher numbers. And so back in 2005, some authorities from New Jersey called my advisor and told him that they are seeing higher gross alphas. And when they look at the isotopes, they found that they have the products of the radium decay series, but they don't see any radium. So if you remember back in the chain, so what mostly they see was this guy and some of those products, but they don't see any radium in the water, which was quite strange, because in order to see the daughters, you have to have the parent, right? But there was no parent in the water. And the levels of the daughters were quite high to create this very high alpha, gross alpha that they were suspecting. And so here was a really interesting case to figure out how do we have the products without the parent. So does anybody have any hypothesis? Actually, this is not published data yet. We're still wondering, and we have one hypothesis, and I'll tell you what we think is causing it. So first what we started, we need to know how much we had to prove that the parent is not there. So we started looking at the radium, and the way we detected is we have developed this method is we take a water sample, about 20 liters of water, and then we have this resin, which is basically plastic small beads that are covered with manganese dioxide. And we put it in a small column, and we just pass the water through this column. And manganese dioxide has very high absorption ability for radium. So without doing chemistry, we absorb just physically radium on this product, on this resin. And it also absorbs radium-226 and all the radium isotopes. And there are two ways to detect this radium isotopes that are already pre-concentrated into the resin. One way is to put them in the specific geometry. We had well detector in Florida. It's small vials that we fill these vials with the resin that already has the radium, and we put it in the gamma detector and we measure radium. The other way to do this is we can strip the radium with acid from the resin and precipitate it on a source, and we can do alpha spectrometry. Right? These are alpha, radium-226 is an alpha emitter, right? And then there's another way to do is just leave the resin in the column that we have and then connect it to an instrument. So radium-226 decays, produces radon, and we have a radon instrument that measures radon in air. And if we can flush and get out the radon from the column and circulate it through this detector, we can detect radon. And when they are in equilibrium with the radium, if we wait a long enough time, we can calculate the radium concentration. And this is how the gamma vials look like. We had already absorbed radium on these beads, and then we put it in the detector, and it's a well detector, and we count. And the spectrum that you look at, you can look for radium-226 either through the peak of at 186 keV when there is no uranium. The resin mostly absorbs radium and not uranium, so that we basically separated this interference so we can measure it, we can calculate it from the 186 peak. Or we can do this through the products. We seal the vial, wait for the 21 days for equilibrium, and use the lead-214 and bismuth-214 peaks, either ways. We usually do this because the intensity of this peak is usually very low, so we like to combine those two peaks for better precision. And radium-228, we can detect it through actinium-228, which is at 911 keV. This is the gamma vial. The detection limits of these methods are quite good. Again, I use this formula to calculate, it's a very common formula to calculate minimum detection activity by using the background of the detector, and we use different count time, and you see normally we are radio people, we know the longer we count the sample, the better the activity. At the beginning is a very steep curve, and then eventually the detection limit levels up. But pretty good detection activity minimum with this method. The third method that I told you, this is the column that we absorb the radium on. We connect this column to tubing. This is a desiccant drying tube. And we connect it to an instrument which is called Rad7, and it measures radon in air. And the instrument has an internal air pump that circulates the air, flushes this volume of resin, dries the air and returns it back, and counts decays of radium-222. And when radium-222 is in equilibrium with radium-226, then you can calculate the concentration of 226. And these are commercially available products after we made the method. So this is my own laboratory column that we made in Florida. But then we published the data, and the manufacturer made these columns that you can buy. And if you have the instrument, these are just simple set of tubings. You can make them in the lab, and you can measure radium-226 easier and cheaper if you don't have gamma spectrometer, because this instrument is only $5,000, and we know gamma spectrometers are very expensive. And in addition, those are instruments. I will show you the rest of my research is based on this small piece of equipment. We take this instrument in the field, and we can attach different adjustments, and we can measure radon in water continuously. So we happen to have like 15 of those in the lab. We could spare some for laboratory experiments like this. So if you're more interested in this method, I can share with you the paper we published. And in fact, this is a PIPS detector, and it gives you spectrum. It not only gives you the radium-222, it measures the products of radon, which are the polonium isotopes 218 and 214. And this is a spectrum coming from the instrument. It gives you first the energy of the polonium-218. And then this is the peak of 216, which is coming from the thorium-232 chain. And then the next peak is polonium-214, which is the daughter of 218, and you have to wait for about 2 hours to get in equilibrium. So it's a quiet, smart machine, very robust, and I highly recommend it for laboratory and field work. And how does it work? So you have the source on this resin, preconcentrated radium on the resin, and then you have this air pump. We said it circulates the air comes out, and this is the chamber of the detector. Circulates air, flushes out the produced radon, which is a gas, dries the air because the instrument doesn't like moisture, and brings the radon inside the chamber. And you have all the radon isotopes because you absorb all this radium on the fiber, right? But it's an alpha detector, it can distinguish different energies, so it will give you counts for each of those isotopes. So the radon isotopes decay to different polonium isotopes, and the surface of the detector is negatively charged, while these polonium atoms have 1+, and they are immediately attracted to the surface. This is a PIPS detector, and they decay here, and this is how the detection of alpha particles is achieved. We know that when we use traditionally in the lab, in the wet lab with alpha spectrometry, we have to create vacuum because of alpha particles recombine to increase the efficiency. This is a very smart way to do it because, you know, there's no vacuum. It's a normal pressure system. Air just circulates. But the polonium isotopes decay exactly on the surface of the detector, and so the alpha particles don't have a chance to recombine. And we have efficiency of about 30% to 40% detection. And so, excuse me, this is a company that makes those instruments, if you're interested in. So let's go back to our case where we were seeing the products, all these products, So we were seeing the products from the decay of radium-224 as thoron and polonium and lead, but there was nothing, we couldn't see anything with our gamma spec for radium-224 and neither radium-228. And we saw some very high levels of those cross alphas. So we had this unsupported lead-212, which was, we would call it disequilibrium. So it's not supported, it's an orphan isotope, right? So a usual distribution system in US and probably everywhere, if you are using groundwater for drinking water, you have the aquifer, which is a source for groundwater, and we pump to a well, and then we perform some treatment, which includes aeration, if there are some gases to get rid of them. Then we do some chlorination, which is for disinfection of the water, and then some pH adjustment if needed. And then we distribute this water to POE, stays here for point of entry before it enters the public system. And then it enters the public system, and then it's distributed to school, private houses, and so on. And we call this point of uses. So point of entry is before the distribution, right? And so most of the monitoring in US happens at this point, not at the point of use where people use the water. And it's pretty much everywhere. You know, the companies who distribute the drinking water, they monitor this point. And they pretty much don't care what people get in this. So when they monitor at the point of entry, the radioactivity was low. But when they monitor at the point of use, the radioactivity was high. So what is going on? So we went to these places. This is again the same instrument I showed you, but now we measure radon in water. The way it works is we pump water to small shower head, and we degas the radon. Remember that the instrument measures radon in air, and so we get hooked to the system. This is a private house in New Jersey. And then we take out the air phase, which is now enriched in radon, and circulate it through the detector chamber. And this is how we measure radon in water with the same instrument. So we measure radium. Apparently now we measure radon. And the levels of radon were really high, specifically the foreign level, the radium-220. And some of the water looked like this at the point of entry. At the point of use. This is a private water that was actually sampled in Florida, in Pensacola, in private school, in the kitchen. And these are some of the results of radon isotopes. So remember, at the point of entry, so they did some aeration and before the point of entry, and they removed some of it, so nothing in here. Then actually from the then they saw some in the point of entry, and then it started increasing even as it goes to different places. So these are high schools, different private houses, and so on. This is for thoron and radon, both started increasing along the line. But the radium isotopes, the parents, were not really high. I mean, there's no trend. You don't see increase here. In order to see the increase here, you need to have the parent increasing here. But it wasn't there. So to solve the mystery, what we think is the case. So what we think is, specifically in old drinking distribution systems, these systems are sometimes 100 years old. And they develop scale, which is coating on inside of the pipes. I imagine this is a pipe. So this scale is mostly based on sulfides and phosphides, and also when these systems are these pipes are metal, they also have additions of manganese, iron. So when this material ages, it produces manganese oxide. Remember that our resin that we absorb to measure radium is based on manganese dioxide. So this is the same material that develops, corrosion material that develops in the pipes. So this material absorbs the parent, radium. But then radium decays to some gaseous phase, which is radon, in this case thoron. And as we flash in the morning our faucet, we flash all this build-up radon, and then radon decays to those products, and they are alpha emitters, and we see them in the water. But we don't see any radium because the radium is in the scale absorbed. That's what we think. But again, I said this is unpublished data, and we are still working on this. So the high thoron that we see, that peak, is because it's produced in situ and the pipes. So I was looking yesterday when I was preparing this talk about the regulations of radioactivity in Peru and drinking water, and I couldn't find anything. Maybe you can give me some information. Well, you probably measure again gross alpha, right?
Yes.
Yes. Radium. Which
Alpha gross.
Gross alpha.
Gross alpha, gross beta.
Gross beta too, yes.
Radium 226.
226, the longest lived. Okay.